All right, so the second part of chapter 17, we're going to be dealing with the application or applying the Fourier series. Very simply, there are four, I think, straightforward steps. You can probably have anticipated these while we were developing the Fourier series itself. So the first one, show the forcing function or functions if there's more than one. Thinking of regular nodal and mesh analysis, loops, nodes, that sort of thing. So you may have multiple sources, right? Show those sources, the forcing functions, as Fourier series. All right. Then transform the circuit to the frequency domain, right? We know about that. Find individual responses for the DC and the AC series components, right? We know, we saw the Fourier series, when it's finally expressed, has a DC component, if there is one, and then an AC component that can be various combinations of sines and or cosines. That means then that we can really treat the circuit with superposition and simply add the individual responses of each of the waveforms. All right, and what we'd like to aim at is just having a DC response, if there is a DC component, and then finding the coefficient and the frequency of the various sine and cosine components. All right. Usually, if you find one, find the coefficients of one. It's really a set of coefficients that change with the number of the coefficients. All right. So now, if we have a forcing function, so let's take a simple example of a forcing function. This one happens to be voltage, but the same representations could be made for current as well, of course. So here we are with a DC component. Let me get my pen and play here. Here we are with our DC component, right? DC, and then all of this is the AC components. And we can think of that as some linear network, right? So thinking of linear systems, these are linear elements. Nonlinear networks are another story. All right, and here's our periodic source over here, and we might want to analyze for the current. All right, this source, namely this thing here, this whole thing actually is this series of sources right here, right? You can tick them off. There's your DC component. There's your fundamental. There's your first harmonic, second harmonic, and so forth. All attached in series, right? Because it is a summation. Okay, by superposition, you can take and solve the circuit one source at a time. So here we are solving it for the DC term. Here we are solving it now in phasor form. Remember, anything that we're good at representing things here. Here is the time domain, right? And we convert that to the frequency domain. And here we are in phasor form with the frequency-dependent terms. There's the next one, different offset. So notice that the full complement is allowed here. Phi 2 or theta 2 is a different offset, right? Here's our basic arrangement. Whoops. Come on down here. Here's the basic frequency as a function of n. All right, and you can go through however many there are, and you will get a bunch of a whole series. In fact, as many as there are in the thing, you'll get a whole series of currents, right? N of them, in fact. And so by superposition, right, we can simply come to the phasor sum. See, here we are back again. This is phasor notation, thinking about it that way. And now notice the type of angle we've changed to a psi instead of the theta, because we've had a z term involved, right? So this is going to probably change the angle, right? Whatever's going on in here. All right. So that's and you've probably been anticipating that, just because whenever you could represent any source or any signal in Fourier form as a Fourier series, you then can decompose it because it's a simple sum. Okay, love that, the way that works. So let's take a couple of minutes and do one of the practice problems. Here's a variation on the one in the Chapter 6 edition. So this is the waveform applied to this circuit. Now, we can find the Fourier series for this quite easily by just using table of 17.3, right? You can just look that up. And this, I've mentioned this before. So many of the waveforms are standard forms. They've already been solved many times. You really just take advantage of those when they're there. And in this case, we're looking at this entry. It's a over 2, where a is the magnitude here. So in this case, a is going to be 6. This is probably a little different than the one that's actually in the 6th edition. The sum of sine n omega 0 t over n. Okay, and we have a is 6, so our real function here is 3 minus 6 over pi times this sum. All right, and we know this is going to be by superposition, just a series of sources, forcing functions. Here's the DC component and all of these AC components. So what we're really going to be looking at is a voltage divider, right? That the V out will be what? Vs of t times the impedance of the capacitor, which is 1 over j omega, divided by the sum of the two, 2 plus 1 over j omega. All right, and we can do our usual factoring with j omega and all that, and we'll get Vs of t times 1 over j 2 omega plus 1. All right, so from there then, we just are solving for the actual specific component or content at the one location. Find it for the nth harmonic, and we've got it, okay? So one thing we'll need then is omega, or omega 0. Where are we? Omega 0 is going to be, what's the period here? Here's the period, right here, this, t equals 1. So that means the frequency is 1. All right, the frequency, if we've got the frequency f0 equal to 1, omega 0 is equal to 2 pi. So now we've got all we need in the piece, and it's just sort of going on and shuffling things around. So let's continue with it down here. That V0 is, we'll just take V0 over Vs and find what we need here. So it's, and I'm really looking at the nth harmonic. I know the DC response. The nth harmonic will be what? 6 over n pi. minus 6, where are we? Minus 6 over n pi. All right, sine of 2 pi n t, and that's our source. I'm sorry, I can take this out. I won't need this. And it will be divided by, or actually multiplied by, our thing going on up here. Whoa, our thing right here. So that's essentially then being divided by 2 j omega is 2 pi, so 1 plus j 4 pi. Okay, so this we can then crank around with all we want. It's what, 6 over n pi at an angle of 90 degrees. So I'm getting rid of the minus sign over there, taking advantage of the fact that it's a sine. And this is going to be divided by, the magnitude of this will be what? The square root of 1 plus 16. Oh, I lost an n in here. 2 pi n. Right. So 1 plus 16 for the nth harmonic. 16 n squared pi squared. And then that will be at an angle of what? The inverse tan of 4 pi n over 1. And this is the nth harmonic. So we can put this together. I suppose really I might not have needed to do this. Where's my pen here? Do this 90 degrees. I could have stayed with the minus sign on the sine. But let's put it all together then. That V out of t is, we've got our DC component, which is with the capacitor going to be an open circuited DC, so that's going to remain 3. And we can say our minus, what, 6 over n pi, right, times the sum of, whoa, I always add that extra little thing on the bottom. I don't know why. This over, so we've got then the sine of 2 pi n t. Whoops, I should put this. And I'm going to take this, the tan of this, so it'll be minus the inverse tan of 4 pi n. Big, long, hairy looking thing, but really it's not that bad. And the denominator will then have this 1 plus 16 n squared pi squared. And actually, you know, I'm going to take this n out of here and put it back under here because we're doing n equals 1 to infinity in there. And we might we'll lose the n out there. So this is what we'll have for the output as a function. Whoops, all of this should be times times. So this is all just in volts, right? Okay, so pretty straightforward. The basic idea is, the ideas to follow are this. You take the waveform and translate it into a series, a Fourier series, and then you solve the circuit over here in the usual way, and then just follow through the math, right? Vectors, just like we did here with the inverse tan and so forth, that we did, you know, a lot with power and those sorts. All right. So we want to move on to power, make some comments about average and RMS power. And for power, we use the amplitude and phase form of the series. You're probably not surprised by this because it's when we dealt with power before, we got AC power, that is, we got into the phasor notation, and that was important, of course. So if we have a linear circuit with this as our voltage description, a DC component, and then the cosine, a set of cosine of multiples of a fundamental, offset, each one offset by a different, potentially different phase angle. Same thing with current, and we'll use the modifier, the frequency modifier multiple m instead of n. So when these are the measurements of a linear circuit, we'll deal with average power. So what is average power? Well, the average of anything is the 1 over the period of it. And here we are with our VI product, and we're going to integrate it over one period and then average it over the period. So that is average power. Well, if we expand that a bit, given our V and I over here, we have our averaging element, the 1 over T. And in the first case here, we've got our DC, the DC power. Okay, basically this is the DC power. And then the AC power is going to be the product of all of these, right? So if we have, where am I at here? We have a DC component in each and then a string of AC components. So we're really going to be looking at all the possible multiplications. And we've taken care of the first one, right, where the VC, we've gotten these two together. Now we can take what? The sum over M of the DC with, so this is the first term. Then we're going to take these two. That'll be the second term. So we're over here with that. There's our second term. The third term will be with the IDC against the variable, the variable voltage. So that's going to be this possibility. That's the third term. And over here, that's going to be, where am I at? That's going to be all of this, right? Not too hard to see. And so that leaves the direct product of the two here for the fourth term, right? And that's, of course, what's going on over here. We've got the double sum of this. Now, if we recall from our tables, again, you'll want to keep those tables handy. The DC power is, of course, the DC power. We have that. These two terms right here, if we look at our table of evaluated integrals, we're integrating across a whole period here. One period. And no matter what the frequency, or in fact, that'll be multiple periods as the harmonics, as we take second, third, fourth, and fifth harmonic. And no matter what the phase angles, if you multiply across or you integrate across a whole period or a set of whole periods, right? So really, instead of saying one here, I guess I should say whole periods. Okay, this whole thing becomes 0. And the same is going to be true here. Yes, here, that's going to become 0. All right, this became 0. Now that leaves us just the portion down here. Well, from those same tables, we know when M is not equal to N, the evaluation of this evaluates over the periods to 0. I shouldn't say it's approximately 0, it is 0. All right, so we are only concerned here now about the term when m is equal to n. All right, so when we do that here, we can be thinking, right, this whole deal, you go into your handbook or whatever, and you realize that cosine A cosine B is what? Cosine A plus B, and I think plus cosine A minus B, right? Something like that. So if we apply that to this with m equal to n, we've got cosine. So let's just take it here. We'll have A plus B will be equal to cosine of 2n omega 0 t, and the phis are the same, the phi and the thetas are the same. So we will have, lost my representation, here we are. We'll have 2n omega 0 t plus, actually it'd be minus theta plus theta. Okay, that'll be the key elements. But as soon as we integrate, this leaves it, this leaves us what? Across whole periods. Across whole periods. Then we have, 0 will be for the A plus B case. The A minus B case, let's have the A minus B will be equal to n omega 0 t minus n omega 0 t. So it will be then, however you want to do this, minus theta sub n plus theta sub n. All right. And so, that's then written. We can combine all that together. And here's the form that you get for that. For our whole thing, we end up with the integral of this cosine here now with our difference, our thetas and phis. Sorry, I needed to keep track of the thetas and phis. Okay? So let's now move on to RMS power. And remember what RMS is. It is the square root of the mean of the square. All right, and I think you can see that right here in this description. Here's the square. Right? There's the mean. And out here, of course, is the root. So what does the problem come down to? It really comes down to finding this square. What is that? All right. So if we take the previous function, I go back to that right down here. If we just try to unpack this thing by squaring both sides, right, we'll relieve the square root. We're going to work our way back down to the squared function. So here is that long thing. We'll just call it the part under the root, right? So it's our 1 over t. There's our mean. But we're really worried about all this squaring. So what's really going on here, you can kind of recognize it, we've got something a0 plus the sum, of an cosine n omega 0 t plus phi sub n, right? And so if you square this, you get the a squared term, and then you get the product of this with itself, which is just down here, of course. And then for the middle term, we get twice. There's the coefficient, a0 times that, and 2 times it. So kind of straightforward, but this is the function. This up here that I've written in is the function. This right here is the function that we're squaring. Okay, so what does that break down to if we keep going with it? This was the upper one here was the integral, right? Don't forget that. This is what we're doing, integrating. The integral across a period of all of this, but that nicely, of course, breaks out to an integral of the pieces. So here's the piece 1. Here's the 2 times piece. And then down here is piece 3, right? So the integration, all we did in this step was break down the integration, or distribute, if you will, the integration across all 3 pieces of that square. All right, so if we reduce all this and we invoke our now familiar things of what is 0, right? We know when we integrate this across the period, we're looking at 0. Okay, and here we're looking at that thing we just did with the a plus b and a minus b. And so when m equals n, right, for m equal to n, that's the case we're concerned about, and it's only one case. We end up with the integral across a period, right, times the cosine of phi plus theta, right? But if you integrate that across a period, the cosine integrated across a period, right? Here's what I'm trying to say. Across a period, the cosine of t is going to be equal to 1, right? That's the area under the curve. So all of that comes out, and we end up with am over t, but n equals m, so it's an squared, right? And that 1/2 comes in because of the multiplication of cosine by cosine. So all of that number 3 term here ends up just looking like that. Very nice. Okay. That then goes to, it's still a summation. Don't forget about that. It's still a series. And that goes to what? If I take the square root of both sides, this is what I get. The square root of the DC term plus 1/2 the sum of all those harmonic coefficients. And that leads us to, that if we think of it in terms of a cap A sub n, remember now this was a phasor magnitude. Okay, and that can be broken down into the component magnitudes. And that's what's being expressed right there. So in the case of if the function, remember this function, right, this is a general representation. So this function can be an I of t or a voltage of time, right? If it is what? The current, you have this on the left, right? This is the current representation. And this would be the voltage representation, right? V of t. Okay. And if we want to choose the power across a 1 ohm resistor, here we are, that is simply the function itself squared, and we end up with this, where the DC component of the power is simply, so there's the DC power, and then here's the AC power, which of course is the sum of the squares of the components. So this is like what the triangle components, right? The phasor, the imaginary and real components. Okay. And by the way, we're talking, don't forget, this is still This is still a series, so each one of these times 1/2 is the harmonic power. And you can imagine, those of you who might be audio buffs, or for the many reasons where you'd be concerned about power in certain frequencies as opposed to other, not just audio, this is true in optics. We want to know how much power is in the green spectra versus the blue or the red spectra, or how much power is in the infrared, the near infrared, that sort of thing. So the harmonic power, kind of important. The exponential Fourier series is, well, maybe we can begin with this. This was a form of Euler's identity, all based around the circle. And it might be good to, let's just say we have this form, and let's look at e to the minus ix. Right, just to refresh you, you probably have already seen this, but it just kind of refreshes where we're going with this exponential. So this is what? Cosine minus x plus I sine of minus x. Right? And the cosine of minus x is what? The cosine of x, right? This is just the cosine of x. And the sine of minus x is minus the sine of x. Minus I sine of x. Okay, so that if I add e to the ix plus e to the minus ix, what do I get? I get cosine plus cosine, so I get 2 cosine of x plus I sine of x. So I'm just going to say plus and minus I sine of x. Right? It has them both. So the plus and the minus will cancel. That will take that term out. And we get cosine of x in exponential form is 1/2 the sum of the positive exponent plus the minus, I exponent, keeping it I and j are the same, okay? So that's what leads to these two equations in the text. If you do the same thing that I just did over the cosine, if you do that for the sine, you'll end up here. You see our x is, of course, our x is n omega 0 t. All right, so that gets us to that. Now, if we take these two, so now what have we gotten? We've gotten from time into an exponential form. And now we take our basic Fourier series. Here's our DC term. Here's our AC terms. All we're going to do is plug in, right? We got cosine n omega t, sine n omega t. We got down here, where are we at? We got cosine n omega t, and we got sine n omega t. So we're going to plug that in. And there it is, all stretched out like that. Okay? And we can take a look at the terms. Here's our DC term, of course, that always comes riding along. There's our 1/2. We can factor that out. Here's our summation over n over all infinity. And here's our sum of terms when you got the j involved, right? So with our positive exponential term, we've got what? Here's our cosine term, and 1 over j times our sine term. So if we bring j into the numerator, that makes the sine negative. And here we've done it again. So now we've taken the difference, but we had j in the denominator. If we bring it into the numerator, it's the plus. Okay, so this is j going to the numerator. That causes the sign change. Okay, so I think we're good with that. Lots of plugging and chugging and substituting, but we're pretty used to that. Yeah, and so now we've got a lot of terms made up of other smaller terms. So we're going to consolidate those, and instead of our little a's and b's, we'll pull some things together, and we'll say that we've got a DC term that we're just going to call C0. That's just a name change. No big deal there. But the others are more important. The coefficients are now going to be Cn for the e to the j n omega t term, and c to the minus n, or we could say c conjugate, for the e to the minus j n omega t term. Okay? And in doing that, we plug that all together. So all this is, right, is the substitution. This is like, I'm going to call it, where's my pen here? I'm going to call this whole thing a cleanup operation. Right, so we get down to here. We just keep rewriting the same term. It looks like these long equations, something big and important must be happening, but not always. Sometimes we're just doing like this and cleaning up. So if there is no DC term, well, actually, if we absorb the DC term by changing our limits here from minus infinity to plus infinity instead of from 1 to infinity, right? Then we've just moved, and the plus and minus on for n isn't going to change the series, right? It's basically just going to include the DC term in a nice, tidy, simplistic fashion here. So we could also we can go about getting our various C's as combinations of A and B, but we can also get them, in this way directly from the integral terms right at the start. Okay, in the same way we got A and B back in the beginning of that. Now I'm just going to pluck this from the text. The exponential Fourier series of a periodic function, so stay with periodic, describes what? The spectrum of f of t in terms of the amplitude and phase angle of the AC components for positive and negative harmonic frequencies. Okay, that's the exponential form. The other forms just stay with positive harmonics. But we're going to see this is really quite okay. All right, so we have the amplitude phase form. So we're back to phasors, right? And they can be seen as, you can see it here, the way it's the amplitude and the phase is related to the A and B coefficients. All right, and that will be twice because we had the factor in there. That will be twice the C type of coefficient. Okay, another way of expressing this is to say the magnitude of Cn, right? The magnitude of Cn at the phase angle. So you're kind of splitting it out and going backwards here, right? A squared plus b squared, square root of that over 2. Right? You're just sort of dissecting or deconstructing the phasor triangle the other way here. Okay. Now back to RMS power. In terms of the complex coefficients, the RMS value of the periodic waveform. So now we're back doing power again, RMS power. This was our basic function. So this is the square, remember? Root, same old stuff, root of the mean of the square. Right? So here we have the square right? And then we'll take the mean of it. So now we have the mean of that. And then, so I'm filling it all out, or the text does, right? Plugging in our exponential form. That's the beauty here. Look how simple right from the get-go now this is. So here I substituted what for dt. Okay, so I substituted for one of the t's. You gotta take some patience here with what you're seeing. So here's what have I done? I've taken the integral of one of these, and I've pulled out the other f of t. Right? This is an f of t. So that's my f of t squared. I really haven't changed anything. I've just continued to kind of deconstruct it in a way that's going to be helpful to me. Well, let me change this and get an eraser in here. I love to be able to erase now and then. All right. So where's my ballpoint? There we go. So now we have the next step in expanding this or working it is just to, just keep working. We pull out the c's. That's a constant. Oops, I'm down here. Here I pull this out, and I pull my 1 over t out. That's okay. The summation is out. So I've really just shifted, right? I swapped these two operations. Put my integral inside the sum and did the sum outside. Can I do that? Yes. I'm distributing the integration property over the sum. And this is just like superposition in a way. If I really have a sum of parts and I'm integrating over the sum of parts, I can integrate the parts and add the result. And so that's what's happening here. All right, that's what's happening in this line. Right, and then finally, I take my integral of the function times e to the j omega t, and here I am with what does that gives me? That gives me c conjugate. Okay, and this pair gives me magnitude squared. All right, and that all comes together to be what? Remember where I started? I started back here. Sometimes we keep pulling all this stuff down, and I've got this. So if I take the square root of that, right, this thing is underneath the square root sign here. I take the square root of that and the square root of the left-hand side, and I've got the RMS of my forcing function, or of my function, whether it's voltage or current or whatever. Now this is a simpler form than we've been seeing, right? So it can also be written. This one back here, whoops, this one back here can be written this way. All right, this is our here's our DC component. Where did the pen go? There we go. This is the DC component. And here's the AC component, right? We know that. And we're working right along with this. All I did, by the way, was rewrite this term back here. And then the power dissipated in a 1 ohm resistor, right? And we do that because if you know what it is in a 1 ohm, you can always, what you really want is the magnitude of the elements. And so we have that here in exponential form. Remember, this all works because these are the exponential constants. We tidied it up. A and B, we worked that phasor triangle and came up with the magnitude, and that was C, the magnitude of the A and B. So let's look at an illustration. Here is a periodic waveform, right, where the period is clearly, what, 10. We can go from wherever you want to measure that. We can go from minus 9 to plus 1. Anywhere you go is 10. And the duty cycle looks like it's maybe 20%, but there's that. All right, so if we express the C of n here, they're what? 1 over t. We're just plugging into formulas across one period, right? So we're taking, this is a full period, but we're just taking it from minus a half to plus a half of the period, and our exponential form, and plugging in our values of 10. T is 10. Whoops. There's t. And here's our f of t when it's valid. So here it's valid from minus 1 to 1. Right? So what is this looking at? This is recognizing that, whoops, I'll go over here. That's the period where there's signal. All of this stuff, f of t equals 0. Okay? So we're just plugging into the formulas that we just derived. And now we do that integration, and it's what? Minus, here we've got our, where am I at? Here's our 1 over minus, this thing comes down 1 over that, times e to that, minus 1 to 1. Plugging in, we get this. This is just straightforward integration, right? Nothing magical going on there. And then all we need to do now is just collect terms. So here we take this is all, what are we recognizing? We're putting the 2, here's our exponentials, let's not lose track of those, multiplying top and bottom by 2, right? And moving the j over here, the minus j over here, but then times the minus on top. We change the order of these exponents. You just have to watch where the signs are going very carefully. And voila, we have right here, we've got back to Euler's identity. We've got exactly this going on, right? Those two guys are going to be equal, right? And that's just another application, a further application of Euler's identity. And omega is our pi over 5, right? Our omega 0. So that's our fundamental frequency. All right. Now, if we're going to take the next step, we need to involve the sinc function. And to do that, by the way, we can just say that our finished function here turns out to be this. That's just plugging in omega 0. All right, but now we're going to want to get involved with the sinc function. And remember, you might first want to remember that the sinc function, see, we're ending up with this. This is why I want to go to the sinc, right? Because, whoa. We're ending up with this thing. What is this? This is like sine x over x. But that's the sinc of x, right? And a few things to remember about the sinc function. Oops, well, there it was. Is that the sinc of 0, when x is 0, normally that could be, right, a limit problem. What happens to it as it goes to the limit? And you got a 0 in the denominator. So you got sinc x, sinc 0, sine of 0 over 0. So you got 0 over 0. A little awkward. It's 1. All right, and the sinc of n pi is 0, right? For n equals 1, 2, 3, 4. So just say the sinc of pi is 0, and all the harmonics are 0 as well. Okay. Now, the sinc function also shows symmetry. Okay. Let's pull up our C of n. This is our magnitude equation. Okay, and the phase can be this. So what we're going to be interested in is, these are what? The component These are the spectral magnitudes, right? That's why it's important. And the phase is for us is one of two types. For this, we're talking about either 0 degrees or 180. Okay. So now let's not forget, this is the example we're talking about. This periodic but not symmetrical waveform. I mean, this all works for symmetrical too, but it's a more interesting example if it's not symmetrical. So let's look at the magnitude function. In other words, the spectral magnitudes that I just drew down here. Whoops, down here. So the magnitude, there it is repeated. But here's what happens if I plot that. Right? Remember this magnitude thing here now. This is what? The sinc. And you probably remember this of n pi over 5. Right? You probably remember seeing something like this from trigonometry, possibly even in high school. Very important function when it comes to the Fourier series and the exponential form. Obviously, we showed one example here right off. It's kind of the principal example, an easy one that comes right off the top. So these values, if you can show the sinc function, these magnitudes, are kind of as percentages or as relative values are right there, including a 0 at 5, right? Even though we're not excluding. Look, here's the fundamental. First, second, third, fourth, fifth harmonic is blank. 10th harmonic is blank. Be interesting to see that, right? Anyway, the illustration, this is a commonly recurring one. The phase now, I'm repeating this, the phase only occurs in two forms. So what does that look like? Well, that just looks like a whole bunch of spikes, right, with nothing happening between plus and minus 5. All right, and then it's fixed. It's either 0 or it's 1. Oh, 180, I mean. Yeah. Okay, very interesting functions, but important. And we will, this will be it for chapter 17. Lots of excellent problems all through it, worked out in examples, and they go through the authors take the trouble to go through the steps in great detail, as they usually do. All right. Next, we'll be pursuing in chapter 18. We'll move on to the topic of properties and just more about the Fourier transform.